So if f is a reflection of the sphere, then the degree of f is -1. So we will draw an example of S2, but it easily generalizes to Sn. So what does S2 consist of? S2 consists of two 0 cells, two 1 cells, two 2 cells. See, this is non-standard construction. In a standard construction, S2 consists of just one 0 cell and one 2 cell. And we have already described this construction before. So let us draw this again. So it consists of two 0 cells. Let us name them V1 and V2. Two 1 cells. Name them A and B. And then it contains the upper hemisphere and a lower hemisphere. This upper hemisphere is 1 2 cell with the edge C, and this is lower hemisphere, say L, with an edge D. So let us now write the cell complex associated. Dimension 2 upper and lower hemisphere generate Z2, C1, A and B are the generators, generate Z2, and V1 and V2 generate C0. So let us calculate the image of delta 1. So delta 1 of A is V2 minus V1, and this is exactly opposite of delta of B, which is V1 minus V2. Notice how the orientations have helped us. So the generator of image is V1 minus V2. So this generator will generate entire integers. Now obviously this would imply the kernel is also Z, because map is acting on Z2. To further understand this, notice that the kernel is precisely the diagonal of Z2, that is where coefficients of V1 and V2 are equal. So it's best to understand kernel and images in terms of maps and free groups rather than in terms of topology. What about delta 2? Now delta 2 of upper hemisphere gives us edge C. And of lower hemisphere gives us edge minus D. Now notice why these signs, although if you see the diagram on the left, both C and D seem to be going in the same direction, but that is not so, and we will see this in a minute. So if C minus D, it will generate image of delta 2, which will be integers, and obviously since it is Z2, the kernel will be Z. So let us see why C and D are of opposite signs. So consider these two orientations of opposite signs. So these are two disks with boundaries and opposite orientation. Now place one disk over the other like a paper folding. So that will give you opposite. So if you stick one disk to another, what you get is a sphere. So that is why C minus D. So if I draw it like this, it is more clear. So yeah, C and D are pasted together. They are just folded over each other. So let us calculate the homology groups. H0 is C0 over image of delta 1, which is Z. So this will just give you Z. H1 should be 0. So let us see it is actually 0. So kernel of delta 1, we have already seen kernel of delta 1 is Z. What is image of over image of delta 2, which is also Z. So we get 0. What about H2? The homology group of H2 is just kernel of delta 2, because after that the maps are all 0, which is Z, which we have just shown. So we have drawn this. So what does reflection essentially mean? So reflection means changing one of the coordinates. So since we are in dimension 2, we are going to change u and l. So reflection is changing u and l. Notice that I'm only saying change u and l. Do not, I repeat again, do not change a or b, v1 or v2. So you change only u and l and do not change a, b, v1, v2. So what are the generators? So generators are reversed in the nth dimension. So basically we are changing c and d. Yeah, the two edges. So c minus d is changed to d minus c. Or c is changed to minus d. Again, you might say we are talking about image of delta 2, not kernel of delta 2. But again, kernel of delta 2 is nothing but where coefficients are equal. Anyway, you would have to change the coefficients so that the sum adds up to 0. So that is pretty much it. Now this is important. So we have changed the generators of upper hemisphere and lower hemisphere. And how did we do that? With just a multiplication by minus 1. And that is why the degree of f is minus 1. Yeah, so see, degree of f is minus 1. Yeah, so now we talk about the homotopic maps again because we are going to use them. So let us first construct a homotopy between f and g. So f and g are homotopic. We have just constructed this between two spaces x and y. So in that case, we have already shown that if the maps are homotopic, degree of f is equal to degree of g. Now we are showing that degree of f and degree of g is either plus or minus 1. So why is that? Now you see fg is equivalent to the identity map from the definition of homotopy. So we have degree of f times degree of g equals to 1. So we have degree of f is d1, degree of g is d2. Then d1 equals to d2 is either 1 or it is equal to minus 1. We are going to use this pretty soon on this slide itself. So now we are going to describe the degree of the antipodal map. So the degree of antipodal map is minus 1, you raise it to n plus 1. So the answer is really simple. It is because it is composition of n plus 1 reflections. Yeah, so let us denote the antipodal map by this minus 1 written in bold, and where every coordinate is sent to its negative counterpart. So let us show how it is n plus 1 reflections for Sn. So let me write this down. So antipodal map is composition of n plus 1 reflections. So we are talking about Sn. So Sn is obtained from n plus 1 reflections. So what you do is you change sign of one coordinate at a time. Yeah, in reflection you change sign of one coordinate at a time. So as we saw in the previous slide, we changed upper and lower hemisphere only because we changed sign of one coordinate at a time. So let us write this down. So we are talking about S2. So we have to start with R3. So you start with x1, x2, x3 first. make the negative sign for x3. This is what we did. We changed upper and lower hemisphere. Then you change sign again. So we change the sign of the second coordinate. Then we change sign the third time. So we have done 3 reflections for S2. So for n, we have to do n plus 1 reflections. And since we have seen that the degree of this is times, so degree of fg is degree of f times degree of g. So we keep multiplying minus 1 with itself. So in this case for S2 it will be minus 1 raised to the power of 3, because there are 3. This is minus 1 times minus 1 times minus 1. So another thing is that if this map f from Sn to Sn has no fixed point, then again degree of this map f is minus 1 raised to the power n plus 1. So this will be easy if we simply show that the antipodal map is similar to the map which has no fixed points. So if there is a homotopic equivalence, then degree of f is equal to degree of antipodal map, which is minus 1 raised to n plus 1. So we will be done. So we just have to show f is homotopic to the antipodal map. So first thing is, we are saying that f has no fixed points. So f of x is not equal to x. So this is our first starting point. Now since it is not equal to x, then we can always draw a line from fx to minus x. Yeah. And this line will never be 0 because fx is not equal to x. So this is the line. So this is given as 1 minus t fx plus t times minus x. This is standard formula where t lies between 0 and 1. Yeah, so this is never equal to 0 because f of x is not equal to x. So let us construct the homotopy now. So this is what the homotopy is from map f to the antipodal map. Yeah, so this is not t of x but t times x. So this is the required homotopy. So you put t equals to 0 and then you put t equals to 1 and you get the required homotopy. So just to complete it, this is it.